Okay, so continuing with 5.5, this is the second part. So remember 5 was talking about the substitution rule. The first part, I did it with indefinite integrals. Now we're going to do it with definite integrals. It's pretty much the same exact process, except that now we have to evaluate the integral at the end, right? We're no longer going to have a plus c. So how does this work out? Well, the rule for substitution, if you have definite integrals, is the integral from a to b of f of g of x times g prime of x dx. So remember, this is just the generic form to use substitution. Right? And what is all this equal to? Well, now we're going to have, because we have limits, we're going to have a and g of b as your limits of f of u du. Pretty much they only added these two little limit parts right here. How does that affect the problem? Well, let's check out a few. So we'll start with this. All right, so here we go. Remember, the substitution rule is just a technique to evaluate trickier or more complicated integrals, right? And as I mentioned in the last lecture, probably like 95% of the integrals that you do from here on out are going to require u substitution. You're not going to have very basic, straightforward ones at all usually. So with the substitution, remember, we're trying to let u equal something so that when we take its derivative, it matches something else in the problem or make the problem easier to work out. Now with this one right here, we have an issue because we have this x trapped inside the radical, right? We can't split it apart. Can't say, oh, this is equal to the cube root of 1 plus the cube root of 7x and then integrate both of them individually. No, remember, you split radicals up when they're connected via addition or subtraction. So that's the problem right here, right? How do we do this? Well, we got to let u be something, right? And before we do that, though, let's rewrite it. How are we going to rewrite it? We're going to rewrite the root in exponential form. This is, remember, 1 plus 7x to the 1/3. The index is your denominator, right, of your radical. So now that we've established that, we need to figure out what is u going to be right here. So in this case right here, we only have one really inside part, right? Usually u is something trapped inside of something else a lot of the times, unless if it's a trig thing, it could be something external. But for this right here, the thing trapped inside is this 1 plus 7x, right? So let's let u equal that. And remember the process was, oh, now you're going to take the derivative of this, du equals 7 dx. So now remember, the goal I mentioned it when we first started this lecture is we want to let u equal something so that when we take its derivative, it matches something else occurring in the problem. Well, the dx is occurring, correct? So that's good. But we don't have this 7, like we don't have a 7 floating right here or here. So what do we do with that constant? Remember, that wasn't an issue, right? You would just basically divide it to the other side or move it to the other side algebraically. So now you have 1/7 du equals dx. And then from here, what was the next step? It was to rewrite our integral that was in terms of x in terms of u. So what's that going to look like? Well, we are going to have a 1/7 that's out there from there. And then we're going to have, instead of 1 plus 7x to the 1/3, we're going to have u to the 1/3, right? Because where's that u coming from? Because we let u equal 1 plus 7x, and the third is there, and then we have the du. So now what about the limits, right? This is the new part of this section right here. With the limits, you're not going to use, we can't put 0 and 1 right here. Why? Because 0 and 1 serve for what variable? X. What are we in terms of now? U. So really important, we need to change the limits right here. or change the limits of integration. Now, how do you do that? Well, you need to look at the relationship between u and x. Where is it? Right here. It's your u substitution. So if our x limit, well, let's look at the bottom limit first of all. When x equals 0, what would it be in terms of u? Well, how can we figure that out? When x equals 0, u is equal to 1 plus 7 times 0. Where am I getting 1 plus 7 times 0 from? Here, right? It's the relationship. It's the u substitution that you initially established. So 1 plus, 0 is 1. So our new bottom limit's going to be 1, like that. Okay? Now we need to figure out the upper limit. How are we going to do that? Same thing. We're going to use that relationship between u and x. So when x equals, what did we have? 1, right? Because that was our initial upper limit. We have u equals 1 plus 7 times 1. What does that give us? 8 right there. So that's your new upper limit. That's a big mistake that a lot of people make when they do u substitution with limits, is that they forget to change the limits of integration. Okay, you cannot use 0 and 1 because that was associated with x only in this case. So again, how do we change the limits? It's always done the same way. You're going to go out there and go to your u substitution and plug in your original limits into that x component that you had right there, or your x's inside your u substitution, and think out your new limits like that. It works like that every single time. So now that we have that, we can go out there and integrate, right? So we have this, I'm just going to rewrite it right here. So what does this equal when we take the antiderivative of u to the 1/3? I'm just going to bring the 1/7 along. Remember, that's going to be 3/4 u to the 4/3, right? And then we're going to evaluate this from 8 to 1. Remember, u to the 1/3, when you take the antiderivative, it's u to the n plus 1 over n plus 1. So that's u to the 4/3 over 4/3. But dividing something by 4/3 is the same thing as multiplying it times 3/4, right? And don't forget that 1/7 that we had to drag along from here. You got to keep carrying it along. So what does this become? Well, we have these two fractions. We can multiply them, right? We can't reduce them or anything. So this is just 3 over 28. And then we have basically, remember, it's the upper limit. So we have 8 to the 4/3 minus the bottom limit, which would be 1 to the 4/3. And we can evaluate, right? These are nice numbers. Remember, what is something raised to the 4/3? Remember, fractional exponents just mean it's like a radical. 8 to the 4/3 is the same thing as saying the cube root of 8 to the 4th power, right? And then minus 1 to the 4/3 is the same thing as saying cube root of 1 to the 4th power. And those come out to something nice. So what is the cube root of 8 to? What's 2 to the 4th? 16. What is cube root of 1? 1 to the 4th is 1. So now we have 3 over 28. And then we have times 15, basically. And then you get 45 over 28. Leave it in this form, right? No decimals, reduce if possible. Don't convert an improper fraction to a mixed number, right? Don't say, oh, this is 1 and blah, blah, blah over 28. So we would just leave it just like this. So as you can see, really the only new additional step when you do or you evaluate integrals, what substitution is, you got to plug the numbers in, right? But you have to change the limits first as you do that right there. Make sure you do that. Okay, that's one method of doing it. Okay, I'm saying one method because there is another way. I'll say or. You'll get the same answer. Let's say you don't like the whole changing of the limits. So this is the same problem, right? We still have to do substitution. You still have to move the 7 over. And we still get this, right? You're still gonna get 1/7, and this is cube root right here. U to the 1/3 du. You'll still get that right there. When you take the antiderivative, you're still gonna get the fourths u to the 4/3 like that. If you notice though, I haven't put limits right here. I haven't put anything, the 0 to 3. I haven't put any of that stuff yet because of this is the second method of how to do this. If you don't like change the limits, you're still going to get the same answer though. So where do you go from here once you get this? This is still 3/28. But now what I'm going to do is I'm going to plug back u in what it was in terms of x. So this is 1 plus 7x all raised to the 4/3. I'll use parentheses. And we're going to evaluate that from 3 to 0. So you notice right here, I use the same x limits, 0 and 3. Why? Because what is our variable in terms of here? X. So what did I have to do in order to keep these limits, the original limits, and not change them? Is that after I took the antiderivative of the u, I had to plug back in what u was in terms of x back into the original problem, or what we were left with. Then it's okay for me to use the original limits. Okay, you'll still get the same answer. All right, you'll still get the same answer as you work this out. Oh, sorry, this 0 to 1. I made a mistake. I don't know why I kept 3, 1, 1, 1. Yeah, you'll still get the same answer when you plug all this stuff in. Because as you can see, what are you doing? We already applied this 1 plus 7x when we changed the limits initially, right? When I rewrote it all in terms of u, you'll still get the 8 right here. You'll still get the 1 right here, and you'll have to crank out the values twice. So again, it's two options, right? One option is to change the limits of integration. You know, when you get to this point right here, again, how do we find the new numbers? You look at the relationship between u and x. Plug 0 in for x right here to get the new bottom limit. And then you plug 1 in for x right here to get the new upper limit in terms of u. Or you can bypass that step and just crank out your antiderivative. But then what you're going to have to do is you're going to have to resubstitute back what u was in terms of x, and then go out there and then use the initial limits that you had of integration. You'll still get the same answer. All right, it's just two different ways. It's easier overall to just change the limits of integration, like change these right here as you're integrating, because it's kind of less work. Because if you don't, then you have to come to this and you have more stuff to plug your numbers into, right? So if you have more things to plug your numbers into to evaluate, that's a higher chance that you'll make a mistake with the arithmetic. All right, so here we go. We have this new one, 0 to 1, the integral from 0 to 1 of cosine of pi over 2t dt. Remember, pi is a constant. It's not a variable, right? But again, we have to use substitution right here. Why? Because we know what the antiderivative of cosine of 1x is, or cosine of 1t, or whatever, a trig function of one of that variable. Right here, we have a pi over 2 in there. We got to deal with that. What do we need to do? Well, let's just let u equal the inside. So if u is pi over 2, then what's du going to be? That would just be, remember, pi over 2 is a constant, so it would just be pi over 2 dt. Well, we need the dt, correct? We don't need the pi over 2 because we don't have a pi over 2 floating outside of the trig function. So we just move it, right? How do we move that over? You just multiply both sides by the reciprocal of pi over 2, right? Which is 2 over pi. So now we could say, oh, okay, we have 2 over pi du equals dt. So not too bad right there. Now, when we rewrite our integral in terms of u, right, we're going to have to change the limits. So we still have this integral of 2 over pi now, and then cosine of u du. Now, how are the limits going to be different right here? So remember, our old limits were 0 to 1. We need to change the limits, right? Why are we changing the limits? Because our integral now is in terms of u, not t. So we can't use 0 and 1 because 0 and 1 were for t's. We're dealing with u's. Where are we going to get that relationship to change from u to t, or t to u? This, right here. Remember, we established that relationship that u is equal to pi over 2t. So when, let's do the bottom limit. When t equals 0, we get u equals pi over 2 times 0. That's just 0. So our bottom limit is still 0. What about when t equals 1, the upper limit? Well, u is going to be pi over 2 times, right, because we're using that relationship, pi over 2 times 1, which is just pi over 2. So there's your new upper limit. Don't forget to do that, right? Don't put 0 to 1 in this case, because that's for the t's, right? We're dealing with u's now. So let's go out there and take the antiderivative of cosine. What is that going to be? That is simply just sine, right? So now we have 2 over pi, and then we have sine of u. Remember, you can check your antiderivative, right? If I take the derivative of this, the antiderivative, I should go back to the original expression, right? What's the derivative of sine? Cosine. So we did that correctly. So now we have pi over 2 to 0 as to how we're evaluating this. So this is 2 over pi. And then we have sine of pi over 2 minus sine of 0. So let's see what happens right here. We still have the 2 over pi. What's sine of pi over 2 going to be? That's 1, right? What's sine of 0? 0. 1 minus 0 is 1 times 2 over pi is 2 over pi. So there is your answer. Again, don't forget to change the limits. I keep saying that because that's the biggest mistake that people make on this. They do the antiderivative part right, they get the u substitution right, but they forget these limits right here, which makes, if you use 0 to 1, you're going to get a completely different answer and a wrong answer. And then you wind up having sine of 1 minus sine of 0. If you have sine of 1, that's pretty odd, right? Normally we have sine of some kind of pi value, radian value. So watch out for that. All right, so now we have this integral from 1 to 2 of e to the 1 over x squared. This 1 over x is part of the exponent. So this problem looks really nasty, right? Worse than the other two that we've done because we only had, an x in one place. It was like inside a trig function or inside of a radical. Right here, there's x's everywhere. It's in the exponent and in the denominator. But definitely, we are going to use u substitution right here. So same mode of thinking. You want to ask yourself, I need to let u be something so that when I take its derivative, it matches something else. Okay. And there's all kinds of options, right? Like maybe you're thinking the e to the 1 over x, the 1 over the x, or just the x squared. But you want to think when I take the derivative of something, its result should match something else in the problem. Now be careful because maybe you're thinking I can let u equal x squared and then du is 2x dx. This x here and that x here and that dx and that dx. I'm good. No, that does not work, okay? This x, in order for it to be good, it would have to be in the numerator. This x, when you take the derivative, where's it popping up at? In the numerator of this right here. So that is not valid right there. If I let u equal 1 over x, or x to the negative 1, remember this is, I'm just flipping this, what's du equal? This is negative 1 x to the negative 2 dx, which is actually negative 1 over x squared dx. This is correct right here because you see when I took the derivative of this specific u or 1 over x, I got the negative 1 over x squared. Now I don't need the negative, but I need the 1 over x squared. So you see how this pops up in the original problem, right? But when you derived that x squared that came out of it, where did it appear? It went into the denominator. So this is the valid u right here. So remember, whenever you're doing u substitution, that derivative, whatever comes out of it, it has to match and it's in the correct place. You can't just say, oh, the same letter popped out. Like here, oh, this letter popped out here, this x and this x, they're the same. No, they're not in the same place. But with this one, this x squared, it appeared here, and they both were in the same place, right? Meaning the denominator in that instance. We don't need this negative though, right? Because we don't have a negative here or here. So I'll just divide by negative 1. So now we just, or multiply by negative, you can do that, right? So now what do we have right here? We just have negative du equals 1 over x squared dx. So let's go ahead and rewrite this in terms of u now. So we have a negative rate. I'm just carrying that out in the front. And then e to the 1 over x is no longer e to the 1 over x. It's u, right? It's e to the u. And what happens to the dx and that x squared in the denominator? Well, remember, negative du was the 1 over x squared times that dx. So we basically just have this left over. So look at that. This integral is much easier to work out than this one right here. But we still need to find the limits, the new limits of integration, right? Got to do that right there. New limits. How are we going to do that? Remember the relationship that we established between u and x. So when x equals 1, u is equal to 1 over 1, right? Because again, I'm plugging this 1 into this relationship right here. That's just equal to 1. What does this become? This is our new bottom limit. Yes, they are the same. That is possible, okay? It just depends on what your u was and what's happening right there. What about when x equals the upper limit? What happens right there? Well, still we're using this relationship between u and x. U equals 1 over 2. Well, that's just a half, right? That's our new upper limit. So this looks a little weird, right? Because the upper is a little smaller than the lower limit of integration. That's still possible. But that negative sign, though, definitely will affect that right there. Don't forget, change these limits. So let's go ahead and take this antiderivative. What's the antiderivative of e to the u? It's just e to the u, right? We still have the negative, so we have negative e to the u, and we're evaluating from 1/2 to 1. So watch the signs right here, especially with this negative. So you're going to have negative and then e to the 1/2 minus e to the first power. So what does that ultimately become? You can't combine these. They're not like terms, right? They're not like terms at all. They have the same exponents in order for you to combine them into one term. So this is just negative e to the half or plus e to the first. So you got to distribute the negative sign into both terms. And that's your final answer right there. All right, so let's attempt this one right here. You try to look at it. Remember, you cannot split this. You cannot say, oh, it's the integral of x times the integral of x minus 1. We're going to have to do u substitution right here. And there's options, right? You may be thinking, do I let u be x or the x minus 1? Now, this one, if you remember, I did a few of these from the last section. It was the very last few questions or problems I worked on, maybe the last 2 or 3, where it was a weird case, right? Because both of these x's were of the same power. If they're both of the same power, but one's trapped inside of like or something, you're gonna have to do that manipulation trick, right? So what we're gonna have to do is let u. And the reason we have to do that manipulation trick is because if I let u equal x minus 1, for example, I get du equals dx, which is fine because we needed the dx. But what about this x piece right here? Where does that get represented with the u? So we kind of have an issue. Or what if we let u just equal x? Well, that takes care of that. And then we get du equals dx, which takes care of that. But now we're missing this piece right here, right? So that's the indicator where, oh, I don't have to do that weird manipulation trick. Now remember, the way you do that manipulation trick is you let u equal basically the one with the most terms in it. So the x minus 1, right? That has 2 terms. The x has 1 term. We're going to let u equal x minus 1. And then we're still going to find the du, which is dx in this instance, right? We still needed that. But as far as this x right here, what are we going to do? Well, that manipulation was where we took our u equation that we created and we're going to solve it for x, right? We can say right here that u plus 1 is equal to x, right? What did I do? I just added 1 to both sides, right, to get to here. And we're going to use all 3 of these when we rewrite our integral in terms of u. So this x, what is that going to be in terms of u? We did that, right? We solved that right here. We manipulated, we added 1, right, to both sides. And that's how I got this, right? So instead of you having x, you're going to have u plus 1. And then instead of us having the square root of x minus 1, we're going to have the square root of u. And then we're going to also have du, right? And then something else that we should change is the square root of u, right? This is no longer the square root of u. Well, it still is, we're just going to rewrite it as u to the 1/2 power. We always want exponents when we're trying to integrate or derive, when we're dealing with radicals. And then we also need to change the limits, right? How do we do that? With that relationship, right? U equals x minus 1. That's the relationship between u and x. Why do we need to change the limits? Because our problem now is in terms of u. So all our numbers need to be in terms of u. You can do that second method that I showed you for the first problem where you integrate and you plug back in your x minus 1's or that relationship you substitute back to x, then yes, you can use the original limits. But this is just easier to change the limits every single time. So when x equals 1, what happens? What's our u limit going to be? We're going to have u equals 1 minus 1. Where am I getting 1 minus 1? It's because u is equal to x minus 1, right? We're plugging this 1 into here. This 1, bottom limit into here. So we get 0. That's your new bottom limit. What about when x equals the upper limit, 2? What's your u going to be? It's going to be u equals x minus 1 or 2 minus 1, which is 1. So that's your new upper limit right there. Now, before we integrate, let's break apart these parentheses, right? Let's distribute the u to the 1/2. U to the 1/2 times u to the first is u to the 3/2. Plus 1 times u to the 1/2 is u to the 1/2. And then we have du. Now let's integrate. So u to the 3/2, the antiderivative of that is 5/2, or u to the 5/2 over 5/2, which is the same thing as 2/5 u to the 5/2, plus this becomes u to the 3/2 over 3/2, which is the same thing as saying 2/3 u to the 3/2, evaluated from 1 to 0. Now what's nice is since that bottom limit is 0 and all these have u's, that's all going to 0 out, right? So we're going to have 2/5 times 1 to the 5/2 plus 2/3 times 1 to the 3/2 and minus the bottom limit, right? But that again is just 2/5 times 0, which is 0, plus 2/3 and 0 to 3/2, which is also 0. But make sure you subtract the entire bottom limit, right? It's important to keep the parentheses signified to you. Oh yeah, I need to apply that negative to everything right here, not just the first term. It wasn't important for this one because they were all zeros, but if this bottom limit wasn't 0, right, these values would definitely make a difference. So now what is 1 of the 5/2 is 1. 1 of the 3/2 is 1, right? So basically we have 2/5 plus 2/3. And when you combine those, you get 16 over 15 as your final answer. All right, let's try this. Let's see what happens right here. So we have the integral for 1 of e to the x 1 over e to the x plus x. So a division problem, right? Again, with integrals, you can't just say integrate division. I'm going to integrate the top divided by the integral of the bottom. It doesn't work like that. Can that? But what we can use is use substitution. So again, we're trying to figure out what can I let u be so that when I take its derivative, it matches something else in the problem. Well, if u equal e to the x 1, get e to the x. So it doesn't really help, right? You can't argue and say, oh, well, like if we take the derivative, you can't say, oh, this e to the x takes care of e to the x. No, right? Remember, e to the x, when we derive, first of all, is occurring in the numerator. So no, okay. What about if we let u equal e to the x plus x, the bottom, really the only other option. So if what is the derivative of e to the x plus 1? I'm sorry, I just said the derivative of e to the x plus x is e to the x plus 1 and then dx. This is correct, right? Because look, we let u equal this e to the x plus x. The derivative of that is e to the x plus 1. Now, when we took the derivative, what the result pop out of? It popped out into the numerator. So we needed that, and we also needed the dx. When y'all see these dx's in the middle of a fraction, it's the same thing as it being in the numerator as well, okay? It's the same exact thing. They just normally put that in the middle of the fraction, but middle of a fraction is the same thing as it being in the numerator, okay? So we have it, right? So this problem looks super complicated, but with a simple u substitution, it became very basic. So now let's look and see, what is this going to be in terms of u? Well, u is e to the x plus x, that's in the bottom. And what's the e to the x plus 1 dx component? That's du, right? Now, in this case, we didn't have any things to divide over, right? Like we didn't have a constant floating out here to divide to the other side. Sometimes that won't happen, okay? But now we need to change the limits. Don't forget that. We have our relationship u equals e to the x plus x. That's our relationship between u and x. So when x equals 0, what do we have? We have u equals e to the 0 plus 0. This is not 0. What is e to the 0? Remember, e is a constant. A constant to the 0th power is 1. So you have 1 plus 0, which is 1. That's your new bottom limit. What about when x equals 1? Well, we have u equals e to the first plus 1. You cannot simplify this right here, right, into something nice. Why? Because remember, e is like 2.71, blah, blah, blah. It's an irrational number. So you're just going to leave it as e plus 1. So it's the same thing, right? You don't need to put a 1 here. It's understood. It's up to you. It's optional. But yeah, our constant looks a little funny, right? Or our limit, it's e plus 1. So now what do we do? Well, let's just plug in all these values. Well, first we need to take the antiderivative. What is the antiderivative of 1 over u? Remember, that's a special case. It's the natural log of the absolute value of u, and we're evaluating it from e plus 1. E plus 1 to e. Not e1, sorry. So we have the natural log of the absolute value of e plus 1 minus the natural log of 1. Now, with the logs, with anything, remember, like radicals and all that, only simplify if something nice comes out of it. Natural log of 1 is something nice. That's just 0, okay? If you type into your calculator, you get 0. Now, what about this? Can you split this up and say this is the natural log of e plus the natural log of 1? No, you cannot. This is not equal to ln of e plus ln of 1. No, you cannot do that with natural log. It's the same thing with radicals, right? Like if this is the square root of e plus 1, you can't say it's the square root of e plus the square root of 1. So do not do this right here. That's as far as you can take this, okay? Unless it wanted a decimal answer, which it probably won't, then you leave it alone. Okay, so this, your final answer is just ln of the absolute value of e plus 1. And that's it right there. Okay, if it asks you for a decimal thing, sure, you would type in ln of e plus 1 in your calculator and hit enter, and it'll spit out some decimal stuff. But this is it, right? You only simplify stuff that comes out nice. Nice meaning like whole numbers, right? Something like that. Whole numbers or positive or negative numbers or stuff like that. But no decimals. We don't want decimals or irrational numbers. That's like non-ending numbers or crazy looking fractions, okay? So this is where it stops right here. That's how you do u substitution when you have limits, right, to work with. The most important thing is this stuff in the blue, right? You have to change the limits of integration. How do you do that? It's the relationship that you got between u and x. Where'd you get that? It's what you first started when you first did the use substitution and you're seeing the problem. And then you plug in your limits right in for those x's, and out will crank out the new limits with respect to u. There is that other method that I showed you for the very first problem, but if you notice, I never did it for the rest of them because it's more time consuming, because you would have to go back in and plug in this e to the x plus x, for instance, into here, and then plug in, the e, do your 0 and 1 and plug those individually back into that equation like that, and you have to do it twice. So again, changing limits is usually the easier way. If you like that other way, that's fine. You can stick to it. Okay, you'll still get the same result. It'll just take a little longer. And again, there's more places for you to plug stuff into. The more places you have stuff to plug into, the more likely it is that you'll make like an arithmetic mistake, right? So with these, as always, I'll say take your time with them. All right. It's not a race. There's a lot of little steps. Some are longer than the others.